Okay, cool. Yeah, so you guys are plunging into chapter 7, correct?
Chapter 8.
Yeah,
Chapter 8 now.
Yeah, you said we're skipping chapter 7.
Yeah.
Oh, wait, what?
Yeah, we're
we're-
skipping
we're-
chapter 7.
Then go
We're
to
gonna
chapter
come back
8,
to it.
9, and go back to 7.
Oh, you're doing 8, 9, then back to 7?
Yeah.
Wasn't it 8, 9, and 10?
It's
Oh,
all
was it
that.
8, 9,
That's kind of weird,
I
but
knew we were doing the alkenes, then the one after that. I can never get the name right.
alright, cool. Well,
Something like
alkenes
that.
are hella fun. And that kind of lines up with the lab, sort of, a little bit, not really. Okay, so, alright, alkenes. Does anybody have any specific questions about alkenes? Or alkene chemistry? Anything? Okay, let me just flip to the end of this chapter. So, missed the last 2 lectures, but are we looking at additions, or no? We're looking at primarily eliminations to form alkenes, correct? Anybody?
We just started, no.
Yeah.
We just started on alkenes.
As in, we just started learning nomenclature.
We just started learning them. All right.
Halfway through Wednesday.
So, all right, before we talk about that any further, actually, does anybody have any questions, lingering questions about chirality and stuff? Yeah, specific question? What about it? Just identifying what the orientation of it is, or okay. So that's a BR up and an H. Wait, let's see it again. BR up and a CL down. Okay, on a cyclohexane. So looking at BR sitting up and CL sitting down. We want to determine the chirality around each one of these chiral centers, our R or S designation. So let's look at the top one first, right? Yeah, because bromine would get top priority. And so we're going to first designate priority on each one of our substituents, going by atomic mass. And let's just put in this hydrogen, which isn't shown in the basic structure. So bromine is the heaviest substituent on that carbon, so it gets top priority. Hydrogen is the smallest, so it gets least priority. And then we have 2 carbons that are attached to it. And so those are tied. So we look at the substituents on each one of those carbons to see which one wins the tie, which one is higher priority. And the carbon that has heavier substituents on it wins. So the carbon down here, this carbon is attached to our chiral center and has a chlorine on it, a hydrogen on it, and a carbon on it. While this carbon up here is attached to the chiral center and has 2 hydrogens on it and is attached to another carbon. So we can see that the lower carbon has heavier substituents and is therefore higher priority. So let's say that this is priority number 2, and you up here are priority number 3. And then so we'll make a circle using the top 3 priority substituents. And we can do this as long as our lowest priority substituent is on the dashed line if it's pointed behind the molecule, which is the setup in this scenario. So we can go 1, 2, 3. That makes a nice clockwise motion. So this is an R center. So our first center, our top one is R. I'm going to go ahead and erase all these notes, and that hydrogen. Get out of there. We don't really care about you that much. So now we have to do the same similar process for the bottom carbon. We look at all of its substituents. I'm going to put in the hydrogen that we don't have drawn in. And so here the important distinction is this hydrogen is on our wedged line. It's pointing up. In the previous example, our hydrogen was on the dashed line. and was pointing behind our drawing. Important. But first, we'll deal with that in time. First, we want to make sure we want to get our priorities set. So chlorine is the heaviest atom attached, that's priority 1. Hydrogen is the smallest atom attached, that's 2. And again, we now have a tie. This carbon's other 2 substituents are carbon and another carbon. So what is this lower carbon attached to? Let's check it out. It's got 2 hydrogens on it, which we don't have drawn in here, and a carbon over there. While the dude up top is attached to our chiral center, and also to a bromine atom, a hydrogen atom, and another carbon atom. So carbon up top is higher priority than carbon, this guy. So we've got highest priority, second highest priority, third highest priority. Okay, cool. So now we've got 2 ways to handle this because hydrogen is in the front. I think really, so yeah, there's 2 ways we can handle this. We could either make a separate drawing over here and just put our substituents rankings on their respective positions. So our wedged line gets 4, lowest priority. Our dashed line gets highest priority. This dude pointing up is priority number 2. This dude pointing out is priority number 3. And we can rotate this so that our lowest priority is in the back. And to rotate it, we just select 3 substituents. It really doesn't matter which 3, as long as they contain the ones we want to move. So I can move, the main thing is I want to move the lowest priority position into the back. And so then the back has to go and move someone else. So I'll just say the back pushes number 3, and then 3 moves to where number 4 is. As long as we move 3 of our substituents and keep 1 in the same position, we're good to go on this rotation. So then I'll redraw this. 2 stayed in the same place. I pushed the 1 over where 3 was. I pushed the 4 into the back. And I pushed 3 to the wedge. And so now we can just go, okay, 1, 2, 3. Ba-doom. And see that that is a nice clockwise circle, R. The other way that's arguably easier to do this is to say, all right, hydrogen's poking up. Let's make a circle from 1 to 2 to 3. And whatever that is, whether that's S, whatever that is, we'll just reverse it in our heads and say, okay, this is going to have the opposite designation. So in this case, we go 1, 2, 3, shwoop. Well, that's counterclockwise. Normally we would say S, but since hydrogen is pointing up, we're going to say that this is an R configuration. And that gives us the same thing we found over there. Yay, confirmed. Both ways work. Yes?
I just swapped the 4 and the 1 and the 2 and the 3. It seems to work every time.
The 4 and the 1 and the 2.
2 with the 3.
Does that seems to work every time?
4.
So you swap these 2 and those 2?
Yeah. So you have the same rotation.
That might work in my head. I don't get it right off the bat just thinking about it, but
How would that work? Because then you would have 1, 3, 2, 4.
So you,
Because he moves all the 4 of them.
Yeah.
That corner.
1.
To see would it still be an S?
I don't know.
It works.
Does it work?
Yeah.
It works.
It does
yeah,
work, but
it does. It works.
I mean, I just have the 1 and the 4.
I just
do
reverse
the
it,
1 and the
yeah.
4, and it would still work. Like if we just leave the 2 and the 3 in their original spots and just do 1 and 4, it would still work.
Wait. Oh
You
man,
can't do that.
I don't know if that would work. All right. I'm going to leave you with my 2 recommended strategies because I can thoroughly explain them. I don't feel like that would work every time, but I don't want to run enough tests right now to do it. If You guys like that strategy? Try it out, test it out, maybe with some like problems that you have answers for. We could try it if we go through some problems, but yeah, we could look at some chiral problems. I was hoping to do more mechanism stuff because that's hella fun. But we can look at other things too. Yes.
Can you do something like that, but with like the chair conformations?
Oh shit.
Yeah.
Yeah, with the chair. Yeah, we can do that with the chair. We good on this problem? Yeah. So we got R and R. Yeah, they're both R. Great. R. Yeah. Does anybody have a specific problem with the chair? I can make one up, or maybe the text. And I can
Something hard. I don't know.
pull one out of there. Let's see if I can find something fun. And the textbook. Herb, what? This is chemical reactivity. We want chirality. What chapter was that even? 5? Going way, way back, right? Because who's got a chair? None of you guys. None of you dudes have chairs. Bunch of weak-faced Wendy's. Okay. Right, so I only see one right off the bat, but let's look at that problem. So we've got, I can draw the same chair as them. That would be super rad. Chair, and we've got 2 equatorial substituents, and then we've got. All right, I can make some up based off of this. This guy, and we're asked to determine what is the relationship. What is the relationship between these 2 molecules?
What number problem is that?
This is problem number 5.57B. Okay, so oy vey, how are we going to determine the relationship between these 2 compounds? That's not too crazy. I guess it's a little crazy because these drawings are kind of annoying to work with, but we can deal with that. Cool. So let's look at our first compound first.
Is that a hexane?
Huh?
Is that a hexane or pentane?
That's a hexane. Sorry, my bottom didn't get puckered well enough. Pucker that guy for you. Okay, cool. So this compound, yeah. Let's determine the conformation around each of these chiral centers. So what I think would help first is to put in the hydrogens that we're not seeing. I'd like to do that because those are substituents that matter. And let's look at each center and put priorities on our substituents. So on this guy, hydrogen, definitely going to be our lowest priority substituent. Our methyl, and then we've got, 3 carbons, 1, 2, 3. Our methyl should be the lowest priority of these carbons because it only has hydrogens attached to it. So you should be number 3. And then we'll compare this carbon and this carbon. This carbon has a carbon and 2 hydrogens on it, while this carbon is attached to 2 different carbons and a hydrogen. So this will be position number 2, and whoops, you'll be position number 2 because this dude is top boss for the center. Okay, cool. So we have priority on each one of our centers. So I'm going to just kind of redraw this now with the substituents on it. And how are you set up? You're a chair, so it's a little bit difficult to conceptualize this in my head, but I believe I can set you up like this so that we've got position number 2 and position number 4 in the plane. Pointing away from us will be this guy, our methyl group, or priority number 3 position. And coming out towards us is this bond to our first priority position. Yay! All right, so that was a little difficult. Just
Isn't everything in a plane though? Oh,
so
the chair
in
though?
this drawing, we show everything in the plane, but that is not an accurate representation of the chair. Yeah, the drawings of the chair we use are not really good representations. This bond is further towards us than this bond, really. We have a weird perspective angle on the chair here. Really need to get a model kit to bring to these so that it can be like, bam, chair. But if I were to draw this more accurately, yeah, I would say that really this is like kind of like a wedged line that goes back, and this one goes even further back still. And then, yeah, these two lines should be parallel. So the chair is not a totally flat shape. It is chair-shaped-ish, kind of vaguely chair-shaped, an uncomfortable chair-shaped. Yeah, and so it's kind of sketchy, but these two, I don't really think, I guess there is a wrong way to do this, but the important thing is to know that this equatorial group is going to be pointing way away from us, so that's easily our back position. And that, yeah, this bond, these two carbons, are in this drawing farther away from us than these two carbons, right? Shit, I guess it's a matter of perspective. That's how I see it and understand it. I guess you could look at it differently, but that's going to blow my mind. It's like one of those, is it a duck or a rabbit things. You guys know what I'm talking about, the optical illusions? Hopefully. If not, Google it. Anyway, we've got this designation. Let's put our lowest priority group in the back and figure it out. So we'll move 4 to the back position. I'll push 3 up there, and I'll push 1 there to where 4 was. So that's going to give us 2 in the same spot. 1's up top. 4 is in the back, just like we like it. And 3 is poking forward. So we can go 1, 2, 3. That's totally counterclockwise. That's S. You're S, dude. And now I'm going to erase that hydrogen because we're not using it anymore. Cool. And so we can do the same thing for the lower chiral center. So we've got lowest priority. The hydrogen's still going to be our lowest priority. Our second lowest priority will still be the methyl group. The carbon that doesn't have any substituents on it will be our second priority, and the carbon that has substituents on it will be our highest priority. Kick butt. So for this one, what? This guy's pointing straight down. Who's in the plane? Well, you're the one who's going to be pointing back. That's what's most important. So I'll do a little doodling down here. I'm going to put 4 in the plane of the board. I'm going to put 3 in the plane of the board, I guess. And then we'll have 2 coming forward and 1 in the back. All right, so we need to rotate these so that 4's, right? 4 is in the back. So we'll move 4 to the back. Do a little rotation like now. That should work. This gives us 1 there, 3 there, 2 still popping out. 4 is in the back, so we've got 1, 2, 3, another S center. Woo! Yes.
So basically, all you have to know is which one's in the back, and then make sure the lowest priority is in the back, and then you're good.
Yeah, same thing. And so just for the chair, though, it is kind of important. You guys may want to find and play with a model kit so you have a better understanding of how these chairs actually work. Because yes, this two-dimensional drawing of the chair is not at all accurate because it is it's very much a three-dimensional shape. what might even be more helpful for doing these, now that I think more about it, would be a Newman projection. I think that would actually probably be pretty helpful for conjuring up these drawings.
Wait, wasn't that S2?
Yeah,
That's S also?
they both
They're both
S. They're both S. It's S for days. If we wanted to do a Newman projection, would that be useful to us? Yeah, totally. So just bear with me for 1 second. If we did a Newman projection looking down this bond, and let's say our eyeball is way back here, and it's looking down the bond like that, I'm just gonna get rid of this loser. We'll pull it back up later. It's not incredibly memorable. Where's my sight line? Over there. Okay. So if we wanted to do a Newman projection for this, looking that way, oof, I gotta think hard about this for a moment. We get our guy in the front, we have a hydrogen poking up who's not shown. Looking at it like that, so on this side is our CH3, right? Yeah. And over, am I doing that right? Let's move the I to up front. That seems less ridiculous. So if our I biscuit is up front, that's more fun. We've got our hydrogen pointing down, our methyl's pointing out this way. Our CH2, who makes the whole ring thing happen, is over there, pointing up like this. And then in the back, we have a hydrogen pointing up. We have our methyl group, our other methyl group pointing in the equatorial position, and another CH2 who helps complete the ring. Okay, sweet. So, is that really helpful? Yeah, kind of. We can confirm our structures a wee bit. It's not that useful. But for the first carbon, for this lower one rather, now we could make a drawing and say, put these two dirt faces in the plane together. So we'll have our hydrogen as our low priority guy, and this dude was our second priority guy. And we can say the methyl group's popping out at us. You're number 3. And the highest priority one is the carbon who's in the back. That wasn't useful. I don't think that was a good use of our time. Sorry about that. Let's screw the notifications. So we have our S and S configurations. Let's just double check the configuration with what, 2 methyl groups, right?
Mm-hmm.
Yep, 2 methyl groups. I can say this is not S, S. And these are not even the same molecule. This is really kind of a waste of time in a sense. But whatever. Yeah. All right. So I want to retract what I just did here. This was stupid. This was pretty stupid. What would have been much, much easier to do? Let's learn from Jake being an idiot. It would be much easier to do, and let's just redraw this bad boy without all this other junk going on. Equatorial. I should have done what I like to do with these in the first place and say, all right, we've got a CH3 here, and that is down relative to this axial hydrogen, right? It's down. This other CH3, that one, compared to the other substituent, is in the up position. So if I were going to draw this on a cyclohexane, I would say, bam, that CH3, it's down. I'm going to give it the dashed line. Ugh, what a dumbass I am. And this CH3 is up. So I'm going to give it the wedge to say that it's pointing up towards us. And that's the easy way to handle this. Not that stupid. Sorry about that, guys. Not that stupid stuff I was doing there. So yeah, when you do see chairs and they are asking you about chirality, use the suite up, down. Is it in the up position or down position? Does it get the wedge or the dash? Use that to help you translate back to one of these chairs, and then your life should be easier for figuring out chirality. Did you question yet?
Yeah, there's a question from lecture that he wanted us to try as a mechanism.
Yeah, let's totally do it. Do you have that
Yeah.
with you? I love mechanisms. I do mechanisms for days. The best. Push those arrows, so good. Oh, sorry, I didn't finish that problem actually though. What was the relationship between those two? Does anybody know?
No, the ice one.
I think you were down and you were up. And these were both up.
Mm-hmm.
So just looking at those, does anybody know what the relationship between these is?
The
Diastereomers, that's right. And the reason we know that is because there's two chiral centers, but in these two compounds, only one of the chiral centers has changed its orientation. So by, make this a little clearer, but by from changing to a wedged line to a dashed line, that changes the orientation in that center. And since we only have one center that's different and two chiral centers total, boom, these dudes are diastereomers. I'm just going to write diast because they all end in areomers or something mers. Write diast, everyone knows what you're talking about. All right, maybe not everyone, but everyone who's cool. Let's look at this mechanism. Oh, yeah, that ain't no thing. I don't need your pencil. Why am I grabbing that? So that was...
I just remember that with computer.
How was it?
It was pretty straightforward. It's like all over.
That was just this, and we're producing the chlorine at the... All right, yeah. So this produces Cl. Okay. Not too crazy. So what I like to do for these, step one, is I like to say in the beginning, we've got two compounds coming together. Which one is our nucleophile and which one is our electrophile? Anyone?
We didn't go over that.
You didn't go over that at all?
Nope.
All right, well, I don't care. This is a really great way to handle things. Does anybody know how we would identify our nucleophile? What are we looking for in a nucleophile?
Is the one that's is the electron loving is going to attack.
Right, it's electron loving. Wait, sorry, nucleophile. It loves nuclei. Phile, love, nucleo, I don't know, nucleo. For the nucleus. It loves the nucleus, it loves protons, it loves positive charges. So guys, remember, the nucleophile loves positive charge. The electrophile loves electrons, negative charge. So which one of these wants positive charge?
CL?
The Cl is right off the bat a pretty good call. I would agree with you if it were Cl minus, but right now it's got a positive charge that it's hooked up with. So our chlorine's actually pretty happy right now. The other thing, so I'll just
The
throw
double bond, right?
Huh?
The double bond's going to attack the H.
Correct. The double bond specifically is our nucleophile. And so nucleophiles, are groups, functional groups usually, that have a abundance of negative charge. And this is either a double bond where there's excess electrons in that bonding region, or anions, species that have a negative charge and lone pairs, or even a partially negatively charged species that has lone pairs. So sometimes we might see like just some plain old water. It's pretty rare, but every once in a while just plain old water might act as a nucleophile, and that's because water has a significant amount of partial negative charge on its, stand over here, on its oxygen. So our double bond, though, double bonds are very good examples of nucleophiles. And what we can look at in the HCl, I'm going to write it a little differently. I'm going to show them bonded. HCl, we have a abundance of positive charge or partial positive charge on the hydrogen. And that's because chlorine is real freaking electronegative. So it pulls electrons towards it when it's in a covalent bond. It pulls electrons like whoa. And it pulls them away from the hydrogen. So we can see double bond, we say, aha, nucleophile. We look at this and we say, ah, hydrogen, who's being de-shielded, who's having its electrons pulled away, totes our electrophile. And other side note, when I'm doing mechanisms personally, anytime I see an acid, I think of this usually as just being H+, especially because we know HCl is one of the strong acids, right? This is an acid who, in water at least, completely dissociates. So it's a lot of the time safe to assume that these folks are going to behave independently. But for a good mechanism, we should show them attached to begin with. But, again, you can usually think of in HCl or other strong acids, think of the hydrogen as getting ready to work on its own. So our first step should be our nucleophile attacking our electrophile. That's pretty much always how the reaction is going to go. A nucleophile attacks an electrophile. Sometimes we don't have that in situations with rearrangements or leaving groups just leaving. But in this case, that's what goes down. So we draw an arrow coming from our nucleophile and going to the electrophile. So in this case, I'm showing the arrow coming from the middle of the double bond because that's where the electrons are coming from. They're coming from that double bond. They're not coming from a specific element, but from the bond. And they're going here, not to this bond, they're going to a specific element, to this hydrogen. And so this is a pretty standard question.
No, just
Cool? Okay. This is a pretty standard proton transfer step. We have to do a little bit more here. We have to show one more arrow. And that's because for every arrow we draw, this generally designates that we're making a bond. And hydrogen cannot have two bonds. So whenever we make a bond to hydrogen, hydrogen is going to break one of the bonds, well, the bond that it already has. Very rare, hydrogen bound twice. So we'll show this hydrogen-chlorine bond breaking. The electrons come out of that bond, and they go on to the chlorine. Boom, kick butt. This is our first step. And this is a very, 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 very common first step for additions. I guess not very, yeah. It's a pretty common first step for additions that you guys will be seeing. We should probably go over some of the other fun addition across double bond mechanisms. Because they're so rad. Anyway, so this is our first step, and now we want to show the aftermath of this. So what does this do? This gives us our cyclohexanes, still pretty much the same, and we've generated, now we're going to generate a carbocation. Since this is not a symmetrical substrate, and since I can't hold on to chalk especially, it matters where this hydrogen goes. It matters which carbon it goes onto. Because we could put it here, or we could put it here. We could put it in the terminal position on this primary carbon, or we could put it in the chain on this secondary carbon. Does anybody have a guess where it goes?
when they go in the middle.
In the middle?
You would have a plus charge in the middle than the, yeah.
Rather than there.
Yeah.
That is correct. Do you know why?
Because that's where it's like electron, that's where the electron's going to go, is like electron deficient in that area.
Correct. This position is more electron deficient than this position. So to make it super simple, carbocations prefer to be in more substituted positions. Let's make it super simple at first. So a carbocation's favorite spot is in a tertiary position. Its second favorite spot is secondary. And its least favorite place to be is in a primary position. Doesn't want to be in a primary position. So it doesn't want to be in the primary position. And that is because it's an electron deficient carbon. It wants to be able to pull electrons from its neighbors. Cool? To help it be like, oh, guys, I'm real low on electrons. Can you help me out? And so when it's in a primary position, it's just surrounded by a bunch of hydrogens. And hydrogens are already sharing with it all of the electrons they have. They're already sharing all of their electrons in this covalent bond. There's no more to give. But when there's another carbon nearby, in this example, or well, so sorry, you don't have three hydrogens. Yeah, wait, your carbon, you got your three hydrogens. Oh yeah, and so we've got a carbon over here who can share a little bit. But in the case of our secondary example, let's make you a CH3, this now has two different carbons who have a fair amount of electrons that can help ease the burden of this positive charge. And in the tertiary example, there are three carbons nearby who all have significantly more electrons than hydrogen to help share the burden of this negative charge. So this is why we have this preference for more substituted carbocations. Yes?
Don't you still have too many carbons on the first one?
Did I?
Too many hydrogen.
Yeah, I did, right, because it's a carbocation. Thank you. I was like, something's wrong here, but all right, I got 4 bonds. Derp, thank you. Yes. Yeah, I feel dumb. Yeah, so primary is not as favorable as our secondary, which is not as favorable as our tertiary. And so that's why we're going to put our carbocation in the secondary position. And I'm going to throw this hydrogen that we just made a bond to here. And there are other hydrogens on that carbon. I don't really feel like drawing them. I'm just going to draw on the atoms that are important for our reaction. So we have our carbocation, we have our hydrogen, and we also have the chlorine ion that we generated. Okay, so very frequently in our addition reactions, at this point, we would show our chlorine attacking the carbocation. But that's not going to give us the product that we want. If we had the chlorine attack now, we would generate this product. So clearly something else has to happen. Does anybody have a guess as to what happens?
The H takes the plus and leaves. Is H the leaving group?
So no one's leaving. No one's leaving yet. Yeah.
Doesn't say the carbocation moves to the
Oh.
ring to become a tertiary carbocation?
That's correct. So what happens is, remember, we just said tertiary carbocations are the most stable. And there is a tertiary carbon right here. So when you have a carbocation that's either in a secondary or primary position, and it's near a more stable position, a more stable carbon, what can happen is we have what's called either a hydride shift or a methyl shift. And this hydrogen can be like, hey dude, I see a carbon in great need of electrons. I'm just going to take my electrons and go over there. So this is called a hydride shift. And H minus is a hydride anion. And here, hydrogen is kind of behaving like an anion. And so we have this shift. And this produces a more stable carbocation. So you will never see a hydride shift occur unless you can immediately form a more stable carbocation. So we've now moved this hydrogen, who became important, over here. And we now have our carbocation in this tertiary position. So yeah, when you see a reaction and you generate a carbocation and it's near a tertiary carbon, some like little bells should be going off in your head. I want to go through a variant on this, but our last step here is now that we formed a nice stable happy carbocation, this one's long-lived, our chlorine sees it and goes in for the kill. So now in this example here, we have chlorine is behaving like our nucleophile. Chlorine is now ready. It's got a full-blown negative charge on it and a whole boatload of lone pairs, making it a pretty decent nucleophile. And our carbocation is an insanely good electrophile. Electrophiles want electrons, and carbon really hates having a positive charge on it. So this carbocation, and any carbocation for that matter, is going to be a good electrophile. Yay! And then we make the desired product and not this one. Those two there. Rad. So this is a pretty good example, yeah, of the mechanism that we see when we attack a double bond, or have a double bond attack a can I say it? Halogen acid. Simple halogen acid. Just let's let's tweak this a little bit real quickly. So if we didn't want to have a hydride shift, if we wanted to just show a methyl shift instead, if we had a methyl group here, a CH3, we can observe a similar phenomena where this whole group moves to the carbocation. And so now we would have a CH3 here, and our final product now would have a isopropyl group instead of an ethyl group. So we see that with carbons as well sometimes. More common is the hydride shift, though. So if you have a carbocation next to a quaternary center, sometimes that quaternary center will be like, let me break off one of my alkyl substituents and give this to you. Sweet.
I have a question.
Yeah.
So what happens to the chlorine?
So, huh?
What happens to like the CO? When you know when the hydride shift happens?
Oh.
What happens to the CO?
The chlorine's just kind of hanging out while that happens. So, yeah, instead of just immediately coming in, chlorine's just hanging out. And this reaction, we probably would produce a little bit of chlorine coming in and attacking this initial carbocation. But this rearrangement is very fast. So, yeah, chlorine's just kind of like, oh, hey, you just did a thing, I'm going to attack you. But it is, yeah, it's just hanging out. It is not doing any chemistry. Any other questions?
Would that be the only product, or would there be some other minor product?
So there would be other minor products. I would expect. Let's get the methyl groups out of here and go back to the original problem for a sec. But the other products, yeah, we would expect to see some of that initial product where the chlorine attacks before there's rearrangement. It's very unlikely, but you might see a just tiny amount of the product from formation of a primary carbocation. But that is very unlikely. That would be like 0.001% of your reaction. This would definitely be your major product in this. I don't want to speculate at the ratios too
How would
much.
that happen?
How would this one form?
The bottom one, yeah.
So this we could form if we generated the primary carbocation. So to get that product, we would still use the same first step, but if we generated from that double bond a primary carbocation and added the hydrogen into the secondary position, now the chlorine is ready to attack there. Yeah.
So either of those could happen, but the top one is most famous.
Yes. This is very unlikely to form. Because, yeah, a primary carbocation is a sad thing. Especially when it's much easier and there's not hindrance to forming that secondary carbocation. When it's like, oh, you guys are next door neighbors and just as accessible, going for that one. Or really, it's more like this carbon does the grabbing more so than this one because the nucleophile is the one attacking. Cool. What? I don't know where we're about that. There's just weird markings in this book. All right, so does anyone have any particular questions or problems they want to go over? Should we look at?
Can we look at more, like one more reaction, like that one?
Yeah, actually, yeah. Let's look at one more addition. Chapter 8 covers eliminations and is it just formation of alkenes or reactions of alkenes? It looks like it's just formation, structure, and preparation. All right, that's wonderful. But we do have some addition reactions. Okay, yeah, let's look at some of these E1 and E2 eliminations, because that's really what Chapter 8 hits on the most. No, I don't want to do that. I really want to quickly go over a different double bond reaction. No, I take that back. Let's look at eliminations. Okay, so eliminations. So we have eliminations. They are reactions that generate double bonds, bubble bonds. I'm just going to write 2 bonds. Nope, that doesn't make sense. I got to actually write the word. Gosh darn it. Or my abbreviation. So they generate double bonds. When we do eliminations, we pretty much always, for our purposes, are going to have a leaving group. On our substrate, or the molecule we're working on. And we're also going to need a base to help us. And so the general setup for one of these reactions, we have our cool leaving group, Lg, and we've got a hydrogen, and we've got some sort of base. And together, these fun friends make a double bond. We've got base grabbing our hydrogen, and we've got our leaving group, who theoretically will have a negative charge. So very, 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 shit, I went off screen. Let me just rewrite these. So this is going to give us, our double bond, our base with the hydrogen, and our leaving group who is negatively charged. Cool. Great. So this is a very, very, very simplistic picture, though. And in reality, the first distinction is we have 2 different types of eliminations, 2 different ways the elimination can go down. And so these 2 different ways are, let's erase you. These 2 different ways are E1 and E2. So what is the difference between these 2? Let me tell you all about it. So the E1, this 1 tells us, the E tells us it's an elimination. The 1 tells us that it is a unimolecular reaction. What does that mean? That means that the slow step, the hardest step in the reaction, is done by 1 molecule alone. And in this case, our slow step is going to be forming a carbocation. So the E1 reaction proceeds through a carbocation intermediate. Which the substrate generates on its own. And we'll look at a little bit more of that. I'll do another example in a second. But to contrast, the E2, still an elimination, but it is a bimolecular process. It is what we call concerted, or it happens in 1 step. The E1 takes 2 steps. If I can write steps, that would be great. So the E1, if we were to do our simple molecule, let's make it a butane. You're a little bit easier to look at. And we'll just say leaving group is our leaving group. We'll write LG. For an E1, the leaving group, we'll put in our hydrogen, who's going to be the key player. The leaving group in our key step just leaves on its own. It takes electrons it has bonded to this carbon, and it leaves. And so this generates the carbocation intermediate. Plus our leaving group. And then at this point, our base attacks the hydrogen. So this hydrogen is now fairly acidic. What do I mean by acidic? It has its electrons being removed from it. And that's because there's this positive charge over here. So this positive charge is pulling electrons away from this carbon, who's in turn pulling electrons away from this hydrogen. So that makes this hydrogen easier to remove, and a base can easily come in and grab it, and that results in this bond breaking and us forming a double bond. This is kind of like the reverse of that mechanism we went over before, right? In the mechanism we went over before, we had a double bond. It grabbed a hydrogen and made a carbocation, and then somebody came in and attacked the carbocation. Here we have the reverse. Somebody's leaving and making a carbocation, and then we snatch up that hydrogen to generate a base. What? Crazy, I know. So that's fun. Super general example. The E2, on the other hand, box over there, is a much faster step. It's bimolecular. So here, this is our slow step. Forming this carbocation is slow and difficult. It does not happen very quickly. But in the E2, we have a better base generally and a better substrate altogether. And so the base helps this reaction go down. So we have our leaving group, we have our hydrogen, and we have our sweet base. And so in this reaction, our base attacks this hydrogen. The bond between hydrogen and carbon breaks, which forms our double bond. And the formation of this double bond kicks out the leaving group. Ooh, squeaky time. So way more arrows, way more stuff going down, all in one step. But an E2 reaction is a better reaction. These carbocation reactions, they kind of suck. These reactions, generally in my experience, show up more. It depends on the instructor on tests, but they're usually better reactions, and I think they come up more often. Perhaps that's down the road. So those are the general differences. I want to see if there's a really great table I can find. No, just so I don't say anything stupid. But I guess not. So how do we know whether or not we're going to have an E1 or E2 reaction? It's a really good question. So the largest difference is damn, I really thought there was going to be a wonderful table, so I just didn't leave out anything. But I'm probably going to leave something out. Great. So when we're doing these reactions, what favors an E1? When we have, I think it actually, I like going through what favors an E2 first, because I like E2 more. But what favors an E2 reaction? Since we have this concerted step, since it all goes down at once, the base is really playing a key role in this. In the E1 reaction, the base comes in after all of the hard work is done. It comes in and attacks this hydrogen that has already, that's already been made more acidic. So this base is a better base. And in an E2 reaction, we need, by contrast, a much better base. We need a very strong base. So that also complicates things a little bit, because a strong base is going to be a good nucleophile in theory, or at least potentially be a good nucleophile. But if we have a very good nucleophile, what can happen is, instead of, oops, you're a hydrogen. Instead of our base attacking the hydrogen, it can just go, never mind, I'm just going to attack here and kick out the leaving group. And this would give us an SN2 reaction, which we'll get to at a later date. So we have this SN2 reaction. So to avoid this, what we need is we need a base that can't do this attacking. And so, does anybody have any idea how we would make it so a base couldn't attack? Any guesses? No bad guesses, unless you just say like trampoline. That would be a bad guess. All right, I'll tell you. The way we make it so this base can't get in there and attack is we want to pick a bulky base. We want to pick a base that is really big and awkward so that it can't get in and attack this carbon. It's harder for the base to come in and attack this carbon because this carbon has all sorts of crap attached to it, right? It has to dodge all of these substituents to get in there and attack the carbon, while this hydrogen is just dangling out on its own. So if we have a big bulky base, it won't be able to attack the carbon that holds the leaving group, but it will be able to grab this base. Fart noises. Yeah, all right.
By bulky, you mean just a higher molecular weight?
I do not. Thank you for asking for me to clarify, because that was not super clear. So yeah, what do I mean by a bulky base? So bases we frequently, strong bases we frequently use in eliminations would be a very bulky molecule is a T-butyl group. So T-butoxide, a deprotonated T-butanol, or a T-butyl group with an O on it, is an example of a bulky base. It's got all these CH3s on it. So anytime this oxygen tries to go anywhere, it's got a bunch of bulky methyl groups that are slamming into other stuff. It's hard for it to maneuver into place. This is an example of a very bulky base. A non-bulky base would just be a methoxy group, or not methoxy, methoxy group. Methoxide. Oh my gosh, super brain fart. CH3O minus. So this is an example of a very slim, slender base. So we would not want to use this really for an E2 reaction because it's too small, and it would compete and try and attack our nucleophile or attack our leaving group instead of the hydrogen or the carbon with the leaving group. What other factors favor the E2? So for the E2 reaction to go down, we need this really cool thing. We need, I'm going to say this right, collinear, yeah. Collinear, start rewriting that, the hydrogen and the leaving group, H and leaving group must be collinear. So what in the what does that mean? Basically, you know, why am I saying collinear when really they need to be in an anti-configuration? If we were going to draw a Newman projection, we would want them to be anti to one another. If I were going to just draw a nice straight stick model, our leaving group and our hydrogen to leave is up there. Let's put some non-hydrogens here. So we have to have this configuration for the E2 reaction to take place. if these two groups aren't in the same plane, the hydrogen that's going to be removed and the leaving group that will leave aren't in the same plane, then this reaction cannot work. So we need them like this so we can get the sweet 3 arrows of success. Base attacking, double bond forming, leaving group leaving, because that's what they do. So all of this is for the E2. And so this coplanar, I guess actually coplanar, not collinear, it's coplanar. You have to be in the same plane. Collinear, same line. That also maybe makes sense, but not quite. So this can get us into trouble if we're ever trying to do an elimination reaction on a ring. This coplanar business and the need to be anti. Let's draw a gosh darn chair. Chairs are nothing but trouble. And Herbert, derp, 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 derp. So let's say we have iodine as our leaving group, and we've got a hydrogen over here who we're going to pick off. And I'll put some CH3s over here so the reaction can't take place on that side. We always need to have a hydrogen on the carbon next to our leaving group. So we can't do an elimination reaction over here along this bond because there's no hydrogens to get pulled off. So if we wanted to do this reaction, you might look at this and say, like, yeah, good to go, bam, awesome, best time ever. It was the best time I ever had. It was free ice cream. Let's put some other substituents on here just for funsies. But this reaction is, at least as drawn, not ready to rock. And actually, let's put you guys in the equatorial positions, because that'll make it dramatic. And it's not ready to rock, because if we drew a Newman projection, looking down this bond, the one that holds our leaving group, and the hydrogen, or the bond, yeah, the bond doesn't hold them, but the carbons in that bond do. We would see a hydrogen pointed down there, iodine out there, and a C with 2 methyls on it over there. You're part of this other ring. And in the back, we have our CH3 up, and this hydrogen here. Cat where? Love cats. And down here we just have a boring old CH2, and these guys both hook up to a carbon over there. Great. So this reaction is not going to fly in this conformation. This ring conformer does not have our leaving group and the hydrogen that's going to get snatched off in an anti-position. For this reaction to work, we would have to change our conformation, and this ring would have to rotate and move all of its big, bulky groups that are in the equatorial positions into axial positions. So if we did a ring flip on this bad boy, can I do a ring flip, please? Thank you. That's, God, I suck at ring flips. Ugh. Frustrating. Let me try that one more time. Do-do-do-do. Shazam. Shazam. There we go. That's like still ugly, but slightly better. Alright, so now this dude's poking its nose up, and this dude is in the back poking down. So now this hydrogen is down in this axial position. This iodine is now pushed up, also into an axial position. This is good. If we were to draw the Newman projection, looking down this bond, with these both in the axial positions, they are going to be anti to one another. I'm not going to get into the whole thing, but this iodine is pointed straight up, and this hydrogen, which is in the back, if our biscuit is right here, this hydrogen is pointed straight down off of our back carbon. They're in a nice anti-position. So now this reaction is ready to rock. Yeah, that's fun for us. And so the result of that is we might end up getting locked into a ring conformation, or some rings, depending on how they are built, cannot react at all. So if this iodine, if I had initially drawn this iodine down here, this would never be able to react. This iodine was in the axial position here. They would not be coplanar or anti. And in the ring flip, the iodine would be equatorial instead of axial. It would be meow in a gauche relative to that hydrogen. So some rings, because of the way they're built, will just be, despite having a good hydrogen and a good leaving group, unable to undergo E2 eliminations. If that is the case, you still could have an E1 elimination. So for an E1, is there anything else I wanted to say about this? I think that the other thing, I don't really want to get into it right now, but the E2 elimination is favors using polar aprotic solvents. What does that mean? Does anybody know what an aprotic solvent is, as opposed to a protic solvent?
Can't donate protons.
Right. An aprotic solvent is one that can't donate protons. I don't want to get into that right now. Cool. I'm going to drink my tea. Does anybody have any questions at this point? Now that we've gone over some stuff, maybe you thought of something that you were confused about. No? Maybe? No? Not just, okay. Mirroring my wide eyes. Weird face. All right, cool. So, E2 reactions. I'm going to look at some problems from the book. Should we talk about E1 reactions? Some. Oh, we should talk about. Yeah. We should. Oh, damn, that's rad. Okay. Cool. Let's delving a little bit further into the E2 mechanism might be good. Yeah. Oh, shit. This book's actually pretty dope. So when we're doing a E2 reaction, let's draw a sweet substrate. I'm just going to use there as an example from the book because it's real good. Got to change a little bit. So when we're doing a E2 reaction, what we want to do for starters great. Okay. Okay. First thing we want to do is identify our leaving group. Great. Iodine and halogens are, in general, pretty good leaving groups. When you see halogens on molecules, especially for problems, you can assume they're going to do some chemistry generally, because they do get out of there pretty nicely. So we identify our leaving group, and this is attached to what we call the alpha carbon. Nope. Wait. No. I'm sorry. We identify the leaving group And whenever we're looking at a specific functional group, the first element it's attached to, is the alpha carbon or alpha position. So we use this sometimes also with, we'll see this later with carbonyls, do fun stuff where we have alpha and beta positions. So in this case, this guy is an alpha position, and everything who's beta, this is a beta carbon, this is a beta carbon, and this is a beta carbon. And so what we want to do is we want to look for hydrogens that are on beta carbons. We want to look for hydrogens, the way I think about it, is we want to look for hydrogens that are a total of 3 bonds away from the carbon, or from our leaving group. So if I were going to redraw this bad boy just a little bit, hydrogen, 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 hydrogen. So when I say 3 bonds away, I mean here's our leaving group, 1 bond, 2 bond, 3 bonds, there's a hydrogen. 1 bond, 2 bonds, 3 bonds, hydrogen. All of these could potentially get snatched up in an elimination reaction. They are all potential targets. And so we want to think whether or not this is going to, we want to determine which one of these are going to be positioned, or be targeted. Where is that graph I'm looking for? That's, okay, great, there's that table. Awesome. Cool. Right, so yeah, we want to figure out which one of these is going to be taken. And so there's 2 different kinds of products we can form here. If we were to take, let me disconnect your circles. If we were to take one of these hydrogens, we're going to lose our iodine and one of those hydrogens and generate a double bond. That should give us this product with a double bond on what was our methyl group. If we take hydrogens from here or here, we'll end up generating the double bond in the ring next to the methyl group. Bam. And so there are our names for these 2 different products. This one is referred to as, am I going to spell this dude's name right? Zaitsev? Sorry, Zaitsev product. Or what you can really remember is the more substituted. And also more stable. While this one up top is our Hoffman elimination product. Are you double N's? Yeah, double N, 1F. Sorry, guy who's dead. I'm sure he's real bent up about that. So how do we know which one we're going to form? We said, huh? Zaitsev?
Yeah.
Zaitsev. Yes. Under ideal conditions, we're going to form the Zaitsev because that is more stable. The only times we're going to form the Hoffman products, does anybody have an idea why we, huh?
No, that's
Is he going to impact this? I think I'm not sure how large of an effect heat has on that, actually. The main impact is he mentioned in here? I don't remember. I'm not sure about that. But the main factor is the base we're going to use. So before I was talking about bulky bases versus not bulky bases, I think I over-exaggerated the competition of some bases. But there's a really rad table that I'm going to copy real quick. This is on page 361 of your text, but it shows this reaction with base. We did not specify, guys. Giving us either this tri-substituted product or the di-substituted product. And so when we're using a small base, you can start with, a relatively little base, a ethoxide base. So when we throw an O- on an ethyl group, instead of ethane, it becomes ethoxide. Generally, we pair this up with somebody, so we get like sodium ethoxide as a common reagent. We're just showing ethoxide here. Let me draw these crazy cats side by side. So this gives us a vast majority of our Zaitsev product. This gives us approximately 79% of the Zaitsev product and only 21%. I think I have those ratios correct. I switched the second digit. 79 and 29. 71 and 29%. And if we start bulking up our base and we use a T-butoxide, this is going to start pushing us towards the Hoffman product. And so this is because this ethoxide has a hard time coming in to attack these hydrogens, and it is much easier for it to attack these hydrogens. There's much less steric hindrance around these hydrogens. There also are way more targets, if we think about it that way. To give us the Hoffman product, there are 1, 2, 3, 4, 5, 6 hydrogens that could be removed to give the Hoffman product. Well, there are only 2 hydrogens that can be removed to give the Zaitsev product. So the Zaitsev is favored when these can be removed easily. But as we start using bulky bases, it becomes harder. And so what's this last one? I don't even know what the name of that crazy claw-looking guy is. But if we have this crazy claw-faced goon, we see a really big drop-off. We barely see any of this Zaitsev product because these ethyl groups that are dangling off the center are flailing all about, making it very difficult for this negatively charged oxygen to get in and attack these hydrogens. So we only see 8% and 92% of the Hoffman product. So a bulky base can be good for helping us make sure we get a elimination as opposed to a substitution, but if we want a specific product from our elimination, we have to consider whether a big base will give us a Zaitsev product, a more stable and substituted product, or the Hoffman product, which is less substituted but theoretically easier to form because we're attacking more accessible hydrogens. Ugh. Zaitsev. Hoffman. Just talked about that. Talked about anticoplanar. Burp, burp, burp. Burp, burp. Yeah, we already talked about anticoplanar. Look. Oh, what a dick. We should talk about E1 a little bit. Unless anybody has any questions about... Oh, you know what? We should, really quickly also just mention one last thing for the E1 reactions. Maybe 2 more things that are fairly important. So we talked about the base. We talked about how we can form it 2 different ways. We should just talk about, I'm kind of going backwards a little bit, but when we look at our substrate, the molecule we're doing our reaction with, we could have this is for our leaving group, right? Yeah. So if our leaving group could be in a primary position, could be in a secondary position, or we could have it in a tertiary position. Primary, secondary, tertiary. And so, depending on which position it is, this impacts the rate of our E1 reactions. What do you guys think? Do you think the tertiary one reacts faster or slower? Slower. That is not the case. We actually see faster reactions with the tertiary substrate for our E2 mechanism. We should also probably see that for the E1 because we're forming a carbocation. But so for similar reasons, because when we are doing our reaction, we have a buildup of, where am I going with this? We have a temporary buildup of positive charge here, right? Am I not saying that like an asshole? Yeah, because we have that partial buildup of positive charge, the tertiary group is favorable. The other reason the tertiary group is favorable, though, has to do with whenever we have an E2 reaction, we pretty much always have competition with an SN2 reaction as well. So I'm pretty sure I mentioned this, that if we have a base, let's give it a negative charge, instead of coming in and attacking a nearby hydrogen, it can attack the carbon this leaving group is on, right? And that's why I said we want kind of bulky bases. We don't want very tiny bases. And so with primary substrates, it's much easier for a base to come in and do this SN2 attack as opposed to snatching off this proton. So two reasons really. Yeah, we have a smaller activation energy here with our tertiary substrate, and we have less competition from the SN2 because as we have a more substituted carbon that holds the leaving group, it is harder for a base to come in and attack. So here, with our primary substrate, our base is like, yeah, I could take that hydrogen, but I could also go right in there, and that would be really easy for me. There's already a buildup of partial charge there. Right. Well, here, the base cannot attack the carbon that holds the leaving group because there's a bunch of big-ass, not even big-ass, but because there are a large number of substituents around it. Yeah. And let's just really quickly, just to wrap up, one more time show the E2 mechanism. So general form for our E2 mechanism, let's put some like fun groups in. Let's put some real life stuff. Let's put in like an ETO-. So if we have these reactants that we're throwing together, we're going to start with our base. Get out of here, you're distracting me. We're going to start with our base. Our base attacks the hydrogen, like so. The hydrogen breaks its bond and forms a double bond. And because we're forming this double bond, it pushes out our leaving group. Leaving group leaves. So we always are going to have 3 arrows for our E2 reactions. The base attacking the hydrogen, hydrogen bond breaking to form the double bond, and the leaving group being pushed out. Woo! I like the E1, or E2. It's fun. More fun than the E1. Let's talk about E1 real quick. Do we want to do that? Sure. 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 Does anybody have any questions, actually? Actually, would it be more fun to just do one or two problems? And these problems all
Yeah.
suck. Yeah, problem? You want to see some problems?
Yeah.
All right, schmucks. Let's really quickly just talk about. Huh?
Sorry, I have a question.
Yeah.
So, in this example, you have, there's basically, I mean, so I guess I'm confused. Like, if there is a, basically the delta negative charge on the VR, why is the living group, why wouldn't that oxide attack that carbon?
So that's kind of what I was talking about here a little bit. How there is competition between, if it comes in and attacks here, this is going to be an SN2 reaction versus this attack, which is an E2 reaction. And so the way we try and control that is by using bulkier bases if there's going to be significant competition. We try to avoid certainly primary substrates. So this one's secondary, so there is going to be a fair amount of competition. And what else do we do to try and control that?
Would you have both products?
You would, yes. You would end up seeing a combination of both products. You would form from this both the, do them down here. You would get both the elimination product, which would just be this simple fellow, for the E2, and you would also generate this ether with the SN2 reaction. Yeah, so both of those products would be formed. Which one you report kind of depends on the question. And it also, yeah, depends on the base. So as we scale this base up and make it bulkier, yeah, we're going to see much more of the E2. What other factors play in there? I'm blanking on what other factors play in there right now. Because I'm a dirt face. Really, it's yeah. So okay. So for a secondary substrate, we do favor the E2. Really, we get in trouble if we're trying to do an elimination on a primary substrate. And yeah, it's difficult for this base to come in. SN2 reactions on a secondary substrate are kind of a gray zone. Yes. Cool? Question?
Yeah, so the leaving group just like completely gets taken out in the product, so you don't have to like add it in or anything?
Okay, yeah. So for a proper product, you should write in the leaving group just kind of on the side.
Okay.
So for a good mechanism, in this case, I would write in plus VR minus, just kind of hanging out. And I'd put a circle around its charge, because I ain't no fool. Cool. Yeah. Let's like go over one or two problems. And then yes.
Just for clarification, if it's a primary substrate, it'll be E2, secondary substrate, SN2?
Reverse that. Reverse that. So for a primary substrate, sorry, yeah, because the way I wrote those wasn't helpful, right?
Yeah.
Sorry. So for a primary substrate, yeah, we're really going to favor the SN2. I'll just write them both, but I'll make a horrible squeak. The E2 is not favored. The SN2 is more favored for this primary substrate. Where in the secondary substrate, at this point, we start to favor the E2 over the SN2. And for a tertiary substrate, we don't see SN2 reactivity at all. It is too difficult. There's too much crap on that carbon for our nucleophile to come in and attack it. It's much easier for the nucleophile to attack a dangling hydrogen. So this is our E2, and this is our next thing. 2 route. Yeah, let's. I didn't really select dope problems from this chapter, but let's look at a few of these. Yeah, you all suck. I like those. Or would you guys like me to talk about the E1 for a second? Problems or E1 prep?
Nah,
Huh?
You talk about E1.
That's
Yeah, let's talk about the E1 for a minute then,
Yeah.
which will probably be a few minutes. So the E1
What do you want?
is going to go through this carbocation intermediate. And that's generally because in the E1 reaction, we don't have such a good base. We've got a pretty meh base. And we have to have a very good leaving group, like a great leaving group. Instead of meh, I'm just going to write poor. Not a very good base. A weak base. That's better. Let's not make it classist. A weak base. And we have to have a great leaving group. And that's because we formed this carbocation. And those are not terribly easy to form. So, other things in an E1 reaction, we frequently run this in a polar protic solvent. Which generally helps stabilize the carbocation and the base who's going to do the attack. Base? No, base is very frequently our solvent. Not stabilize the base. Take that back. So, who's a fine example of a E1 reaction? So let's put in a really dope leaving group. Last thing, it's going to favor, unless I'm saying something hella stupid, since we have this carbocation intermediate, we're going to favor a tertiary substrate. So we want our leaving group on a tertiary carbon. So we can form one of these nice happy carbocations. Sweet. So we'll work with this molecule, and we'll say that we have an OTS group. That's a tosylate group. Basically, if you see TFs, you should be like, that's so good at leaving. That thing just like leaves on its own. I want to take a brief moment to say what makes a good leaving group. A good leaving group is a molecule. First of all, it has to be basic. This is why I totally should go through chapter 7 first, because it introduces half of these concepts. But a good leaving group should be basic. It should be able to form. Shit, there were some joke rules that I was gonna go through, but then we didn't look at them. Oh, am I right there? Yes, thank goodness. So yeah, it should be basic, or be a good base, and it should be very stable. Oh, so you guys are treating them like acids. That's interesting. Yeah, basically it should be stable on its own. So very common good leaving groups, again, are the halogens, I-, Br-, Cl-. H2O makes a good leaving group. So if we can form a neutral molecule or a common anion, that's great. Bad leaving groups, on the other hand, I'm sorry, when I wrote basic, they should be, I meant to say that a good leaving group should be weakly basic. So it's not something that's going to run around and grab protons on its own. It should be something, again, that is weakly basic. It is not a good base. A bad leaving group should be a bad leaving group is on its own a strong base. Is unstable, and let's just look at some examples of that. So bad leaving groups would be like an ethoxide or any negatively charged nitrogen species or OH minus. These are bad leaving groups. These are guys that are not just going to pop off on their own. And the tosylate is a really great leaving group. So for our E1, question or just head wipes? Okay, so for our E1 reaction, it is 2 steps with this carbocation intermediate. Our first step is our leaving group, just leaving, which is the same thing as the SN1 reaction, which we'll talk about some other time. And so for this, it's important to identify your neighboring hydrogens, because those are the dudes who are going to get plucked off. So our leaving group leaves, and we generate our carbocation intermediate. And now let's just throw in our base that we can use. So we can use pretty crappy bases for these reactions. For an E1 reaction, we usually do use a really crappy base. And water is a pretty crappy base. But once we form a carbocation, water is good enough to do the job and deprotonate. Let's throw this as the other hydrogen for simplicity. So it will attack a beta hydrogen. I didn't get into that. I just kind of trailed off on that alpha-beta thing. But if this was our alpha carbon, this is our beta carbon. These are beta hydrogens. So the weak base will attack a beta hydrogen, and that hydrogen's carbon bond will break to generate our double bond and make this carbocation nice and happy. So the E1, I don't think there's as much. I guess, yeah, I think the E1 is simpler. I guess because it's 2 steps and there's not as many arrows running around at once. But the important thing to know for this is that we have weak bases. So our bases that we use for E1 reactions frequently don't even have a negative charge. They're just like, I could take a hydrogen if it was easily available, but I'm not going to work for it. Yes?
So it would be plus OTS with a negative
Yes,
charge?
thank you, yes. So yeah, we would have plus the OTS with a minus charge, and we would also have plus H3O plus, because we have to account for all of our charge. This guy also picked up some acid. So we started with neutrally charged molecules and no overall charge in our reactants. There should be no net charge in our products. Good pointer. Catch. Thank you for helping me not be a lazy schmuck bag. All right, yeah. Let's look at 2 or 3 problems, and then I gotta get going to a show. So what were these problems that I was looking at? Gosh darn it! I flipped away. Jake, you're just the worst ever. No one likes you. Cool. Oh, that's actually pretty intensity. Screw it. Let's look at a few of those anyway. So I want to look at problem 877 for starters, which is going to be a comparison. We're going to try and determine on a few of these molecules whether we're going to favor an elimination reaction or a substitution reaction. And I know we don't know a ton about substitution reactions yet, but from what we've discussed today, we should be able to make some decisions on these. So this is problem 8.77, and let's just look at A for starters. We have broken chalk. This substrate, Cl, and we are reacting this with TBUOK. What the heck is TBUOK? Does This is potassium T-butoxide. So the TBU tells us that we have a T-butyl group. This is going to be attached to something. And we see that it's attached to an O, and that's hanging out with a K. So whenever we see oxygen with a alkali metal anion, or hooked up with an alkali metal, we're not seeing it as an anion. And also, alkali metals don't form anions, they form cations. Anyway, anytime you see oxygen with a metal, we can assume that that oxygen has a negative charge on it, and that the metal has a positive charge. So that's what this reagent is. And we're asked in this problem, are we going to favor a substitution or an elimination? And so for starters, does anybody want to come and draw what our potential substitution product would look like? Anyone want to be a boss? Stand up? No? Maybe? That is a definitively no face. Yeah?
I'll give it a try.
All right, cool. I think.
Once.
Yeah, right?
Actually, fuck it.
Nah!
No, all right, I'll do it.
Come on, man. Getting stuff wrong is like how you get right later. The more you screw up, the better.
Okay, so this is it, right? This.
Mm-hmm. And I would just use this drawing of it because that's easier. First things first. Well, yeah, important.
So I don't know what so is
It's this guy.
okay, so it's.
Yeah, it's just this dude.
Okay.
That's our nucleophile.
Okay, so.
Because it's got a sweet negative charge on it. Negative charge on the oxygen, nucleophile. Oh snap, you even got the inversion of symmetry in there. Nice. Close.
Plus
Close.
Cl minus.
Yeah, so
Oh, yeah,
not a
Cl.
Cl, that's going to be a hydrogen in there. So this would be our substitution product plus the Cl minus, but
Okay.
inconsequential, more or less. So this would be nice, our substitution product. And you did a really good job showing the stereochemistry. I wasn't even going to get into that at this moment. But anytime we have an SN2 substitution reaction, we see our stereochemistry, the dashed and wedged lines, the way our bonds are oriented, we see that become inverted. So before we had our fun functional group pointed forward, after an SN2 reaction, our functional group is going to be pointed backwards. And we'll talk a little bit more about that going on and what's going on exactly there later. But so this is our potential substitution reaction. And just to show the curved arrow formulas, this guy would attack in there and go up there. Meanwhile, our elimination, I'm going to just draw that one myself because I'm greedy and want to be the center of attention. Our elimination reaction, there's actually two potential forms. We could either have our T-butoxide attack one of these hydrogens. The hydrogen breaks to form the double bond. The double bond drives out the leaving group. And that should give us this plus Cl minus plus T-butanol. We should also, yeah. And we could also potentially attack those hydrogens to get this product. So this would be a minor product, likely. Would it? Well, that's our Hoffman product. Yeah. T-butoxide, it's kind of bulky. Yeah, I think that would be our minor product. So, do you guys think we would go for a substitution reaction or a elimination reaction? Let's ponder for a second. What impacts these? We talked a little bit about it earlier.
It's a huge base,
Right, we've got a big base, so that's one thing that's a factor. So base is one factor. The other factors are substrate. What kind of carbon we're on, whether it's primary, secondary, or tertiary. So we have, what is this, primary, secondary, or tertiary?
Second.
Secondary. There are, wait, what?
It's one.
Yeah, there's 2 carbons coming off of this. There's 2 carbons coming off of this center. So it is a secondary carbon center. Yeah. So a secondary carbon, do you guys remember, is that better for an elimination or a substitution? SN2 or E2? It's better for the E2, that's right, because it's hard for a base to come in and do an a substitution on a secondary center, a secondary carbon center. So because we have a bulky base and because we have a secondary substrate, this will definitely favor the elimination reaction. Yay!
So basically, a CL is CL is leaving.
Sorry, what?
It's-
Yes.
So CL. So it basically attacks the bottom hydrogen, which makes a double bond, which kicks the CL out.
Correct.
3
3 atoms.
Yeah, is the K
Where
still
does
there?
it?
Hey, where's the
where does
K?
potassium-
Oh, yeah, the K should still be in there. I just didn't. Drew it in the front and then just totally forgot. Yeah, the K should also be here. The K is just going to be a spectator ion, which potassium pretty much always is. If you guys think back to general chemistry, you can remember that the alkali metals really don't do much reactions. They're spectator ions. They just kind of hang out and they're like, all right, I helped chauffeur this reactive chemical to the party. I'm just going to hang out now and drink some punch. Man, I'm just killing the chalk. Chalk murderer. Any other questions? At this point, I want to do one more problem. Just for funsies. Just for funsies. Shoot. Let's look at... No, let's not look at those. Those are integrated. It's a pain in the butt. All right, maybe we won't do anything else because the phone's ringing and I can't be held accountable for that. No. Let's look at problem 863B. Predict the stereochemical outcome for each of the E2 reactions. Yeah, that sounds dope. And it looks pretty dope. Hopefully, I'm not making a big mistake here.
Wait, what problem is this?
This is 863B. 863.
That's 36.
That's backwards.
Shoot, man. Thank you. 863B. And so we've got bunny ears on you. Have a CH3 there and a Cl and a CH3, and we are attacking this with NaOH, and we are asked to predict the stereochemical outcome for each E2 reaction. So we're told that this is an E2. That's fun. So our first step should be seeing, all right, which hydrogens are there for us to attack? We want to find all the beta carbons and look for any beta hydrogens, right? Because that'll help us figure out what potential products we have. So this is our alpha carbon. So that makes this a beta carbon. That makes this a beta carbon. And that makes this a beta carbon. So this beta carbon has no hydrogens on it. So let's not even worry about that one. Who cares? This guy has a hydrogen on it, while this dude, okay, so it's good to go, and this one has a few hydrogens on it. We don't have a bulky base. NaOH is a pretty small base. It's a pretty strong base too, fairly strong. So would this favor the Zaitsev product or Hoffman product?
The hall. No.
The Hoffman. So rather, instead of using old dead people's names, would this favor our more substituted product or our less substituted product?
So it'll actually go in and attack the leaving group instead of the
Uh,
outside group.
Not talking about competition with attacking the leaving group. Just saying, would this favor attacking, pulling hydrogens off here, or this hydrogen here? Yeah.
Well, I was going to say more substituted one.
The more substituted, that's correct. Since we have a small base, OH is pretty small, it can get in and attack wherever is best, ideally, and since we're only told to just consider the E2 reaction here. Also, this is a tertiary carbon, so there's no way we would have an SN1 competition. So we're only really going to be able to see E2. And since NaOH is small, we should go Zaitsev or more substituted. More substituted. And that means we're going to pick off this hydrogen here. So we can stop thinking about this one. Okay. So they asked us specifically about stereochemistry, though. And we can see chirality here. That makes me think that there's a little bit to this problem. We should double check what the configuration is here, because if, depending, I'm going to use my words correctly, since there is only one hydrogen that we're going to be picking off, one beta hydrogen, in our selected site, our molecule has to be in a very specific conformation. This only hydrogen has to be anti-coplanar to this leaving group. Oh, and they already are? That's not bad. Ain't no thing. So we just need to make sure that when they're in the right conformation, that they're in the right conformation. Because depending on what conformation they're in, we could have a molecule that looks like this guy with this CH3 here, and the bunny ears, blam, and then we've got up here a CH3 and this. So we could have this molecule, or we could generate this molecule. So these are two different molecules, right? Here we have different isomers around this double bond. And so we need to double check this guy to make sure that we generate the correct isomer. So we do have, these are coplanar, I believe, anti-coplanar, because our chlorine is pointed forward and our hydrogen is pointed backwards. So that's coplanar. If we really wanted to, we could rotate our molecule around so that they're both in the plane positions, if you find that more helpful. But I'm just gonna run with it like this, I think. I'm gonna rotate it because it's gonna make my life easier. So I'm gonna rotate both of these centers so that the chlorine is in the planar position, and that the hydrogen is also in the planar position. And we're just gonna rotate along this bond. So I can move hydrogen to there. I can move this guy up to there, and that dude to there. And on this side, I'm going to move chlorine to there. This guy's going to move to there, and you'll move to where chlorine is. Oh, that's a little complicated, but let's just redraw it. So we've got this bond in the middle. I said I'm putting hydrogen in the plane. I said that this ethyl group is moving up to the wedge. I'm just going to call you an ET now. And we said that the methyl group moving into the back, beautiful. And over here, we have chlorine moving up. We have this crazy thing. Oh, you're just an isopropyl group. You're not that crazy. Isopropyl group moving to the back. Oh, wait, not isopropyl. I'm sorry, T-butyl. Just a T-butyl group. And who moved to the front? Our CH3 moved to the front. All right, cool. So now those are anti-coplanar. And now this is, for me, it's very easy to figure out what our product is. When this is removed by base, our OH minus, it's going to come in, swoop you up, break that bond, break this bond to make the double bond, kicked out our leaving group. We can say, all right, these groups are both pointing forward at us. They're both going to be on the same side of the molecule. So our ethyl group, ET, this guy, in case anyone's a little confuzzled about that, I instead of drawing this group, I just wrote ET for ethyl. That's going to be on the same side as this methyl group on the other carbon. And this isopropyl group, stop saying isopropyl. I'm sorry, that's a T-butyl group, will be on the same side as this methyl group up here. So, by making sure that we have a nice drawing where our hydrogen, who we're picking off, and our leaving group are anti-coplanar, we can definitively determine the stereochemistry of our product. Yeah, with great certainty. Destroy all the chalk. Are there any questions on that problem?
So for this, like, just maybe my conception problem, but like you just want the biggest things, like anti-coplanar.
It's not the biggest things. It's our leaving group and the hydrogen who's being attacked need to be anti-coplanar.
Okay.
So we're not concerned at all about sterics or other crap, bit bulky groups right now. We're concerned with just to get an E2 reaction to work, we have to have this anti-coplanar configuration. And that's why I did the rotation. Because the reaction only occurs when they're in that shape.
Okay.
Yeah, so
Leaving group and beta hydrogen have to be.
anti-coplanar. The reaction, yeah, it can't happen until they twist into that shape. So it might be a reaction where they, to get into that anti-coplanar, they have to make an otherwise unhappy conformation and like push bulky groups towards one another. Like in this case, I guess it's not super crazy. No, this isn't actually too bad of a conformation. But you do have to push bulky groups towards one another. So normally, this hydrogen would probably. I don't think this is a great example.
Yeah, but I got it.
You got it? Yeah. So our most stable conformation may not be ready for the E2 reaction. We may have to rotate around.
So basically, coplanar, you mean they have to be like on the plane.
In the same plane, yeah, and anti. So,
Yeah, I got
so
you.
they're all both in the plane of the board, and they're
I
anti-relative
mean,
to
what
one
if you
another.
didn't? Because one's going back. So one's like coming at you like this, one's going back,
The complete.
right? In that first
In
example?
this first example.
Yeah, one's coming out at us, the other one's going
Yeah.
back.
I think this would have worked. I don't think we really needed to mess around with this
Yeah,
too much.
I mean, because they're still like, if you
Yeah.
look at it from a side, they still be coplanar.
Yeah, right? There's still
If you
anti-coplanar
look at
here.
it like from an angle.
I think, yeah, it's just a perception thing. And
I don't really want to sit
I
longer, so
got anxious and was worried I was going to screw it up, which is why I did the rotations.
Yeah,
Because,
but so if you like, if that group
You
would
just
have
always ask the questions.
OH would have came and would have kicked that, they would have kicked this
Always
H
asking
out.
It's a good thing.
oh, yep, would have come
And
in.
you got this guy kicking
used to
this
never do that
out,
when I
which
was
would
in
have
high
put
school.
this out. That-
Ask
I was
questions.
yeah, I was
No,
terrible.
you
But
do
see,
that.
You would have this
yeah,
out.
no, not really.
No.
I'm so loud, like, what are you talking about? What?
So in
I
this
don't
one,
like
we've
that
got
level of teachers.
this on the same side, the CH3 on the same side as the
That
ethyl.
depends.
You get along.
No.
This is going to give
I
us
would get along with
the
him.
same
Totally fine.
product, I
Totally
think. It's
fine.
just a
Never
little bit
will.
harder to conceptualize. So
No.
now we have these
It's
two on
easier to
the
talk
same
to
side.
than-
Yeah, like that's what I'm saying, like based on
And
like
these
if
two on the
but
same
I'm
side of the
teachers in like high
molecule.
school.
So
were
that
great,
should
like, I
give
love
us,
them. But
We don't bond when
Go
you're
around
running
here.
it away, right?
no, I'm
CH3 is there,
Are you really?
and,
You never told me that.
wait,
Oh, I DJ Nathan.
this should be,
North Osh.
should have that, and,
Yeah.
Yeah.
It doesn't have that Philly accent.
So that's-
I've always wanted to
That's the same product.
And same thing, yeah.
yeah, so these are anti-coplanar. I just think it's a little bit
Baseball, I think.
weirder to look at this.
You're a hippie.
It's harder for me to
I'm
look
not
at this and
hippie.
immediately
That's
know
smart
how
enough
to get to
do it
that.
correctly. Which is why-
And which is why I went through the
which is why
rotation.
I'm not here.
Oh.
Somebody
Yeah.
will like this stuff.
But this does work.
I mean, so if you have one going to the
No, that's
back,
random.
one coming
That's
out,
worth it.
Yeah.
that means that
So
you can
it's
imply
badly
that
geared.
whatever, like.
That they're
Oh,
anti-coplanar.
Well, if they're going, if they're
I
both
also go to
going back.
If they're both going back, deal breaker, yeah.
Yeah.
Then you have to do a
Or if
rotation.
they're both coming out towards you.
Yes, if they're both in the same, unless they're in opposite positions, really.
Oh, really?
So what do you, like, what if this was coming out of that,
Yeah.
you too?
I'm not good at it.
So,
But
I have to
they're,
go.
but they're opposite each other,
Here, why
right?
don't you
And
draw
then
me?
transfer on to other transfer.
I mean, what if,
I can
What
tell you're
if
from
instead
California
of-
because you actually pronounce Trenton
You
correctly.
have-
Like you say Trenton, I just say Trentons.
PH?
Yes.
I just
I think most
Gross
girls
Philly accent talk.
Yeah.
Trent.
Yeah.
Friend. Just gotta slur all your words together.
Just don't say anything.
When you said ET, I really thought you were gonna go with an extraterrestrial joke. I was waiting.
I know, I was really
hoping-
confused. I was like, are we
hoping-
talking
No.
aliens now? Like,
No,
Dude, I got a legitimate question. So like,
no such thing.
I know, they don't like this, but like for this stuff, are we gonna like we didn't even like learn it yet.
yeah, we didn't learn this yet.
In
He hasn't
lecture.
gotten this far, and I don't
So like
think
my
he's gonna
mind
get this
is
far tomorrow
mine
either.
like it's kind of like just going back and forth right now because you put a lot of new topics in my head right now.
Yeah.
Not that that's a bad thing, but I'm just like
So is this gonna be our quiz on the, like, when's our quiz also? Because he told
it's
us.
Wednesday.
Okay, he told our 10 o'clock lecture Monday.
Oh,
Maybe he's doing them
Yeah,
different
for the
days.
quiz, I don't know if I should study for chapter 5, 6,
It's
7.
5, 6,
8, 9,
it's
10.
You
5,
didn't
6,
really-
and then
oh.
whatever we're learning at 8, because he said it goes up to the lecture tomorrow.
okay.
So
How
it
does-
is nothing. for
So
the-
the sixth thing
That's-
is
That's why everyone said, like, I asked, 'cause
Yeah,